Hello, everyone. My name is Tobias Tangström. I work on product management for Amazon Aurora, and we're going to spend some time today looking at global database for Amazon Aurora. So we'll start with a quick recap of database internals. It's related to how we actually do global database for Aurora, cloud native database architecture, and then we'll dive into global database and also look at some features we've released fairly recently around write forwarding, managed RPO, and managed planned failover. But let's start with the database internals. So first of all, traditional database architectures basically include a compute part of the database and storage. And there's tends to be a lot of debate about what's the most important thing in a database. And for sure, folks that work a lot with storage will say that it's all about I/O. And let's say that it's a huge thing with regards to database performance. Availability and durability is related to I/O. So I/O is absolutely critical. And over the last 4 decades or so, there's been a lot of investment just along the database industry in increasing how much I/O you can do and increase or decreasing the latency for I/Os and trying to decrease the number of I/Os that you do in order to optimize database performance. And just a quick recap on a fundamental part of a database, which it's one of these favorite childs that has many names, so can be called write-ahead log, transaction log, database log, and so on. But it's really about capturing all of the changes that happen in the database to be able to maintain database consistency along transactions. So it's based on this do, undo, redo protocol, which basically takes the old state of a page or data in the database, does something, and then you get out the new state as well as a log record. And over time, databases then make changes generally in memory and write to the log on disk to guarantee that data isn't lost. If you update all of the data pages on disk, that's generally a big performance bottleneck. So you want to avoid speaking to the disk as much as possible. And that's why sequential writes to the log is the main form of durability for a database. And then in order to support better performance for reads, once you have to hit the disk, databases tend to issue checkpoints every once in a while to basically keep data pages up to disk, and then they can write those sequentially out versus randomly writing data pages when the changes happen. So if we go and look at this, there's the two things that we do. One is the redo protocol. So on the previous page is the do, which is, okay, you did an actual change to your database. So redo and undo are used. One is when you want to recover a database after a shutdown or a crash, and also undos in forms of rollbacks of large transactions. So when your database starts up, it goes through the transaction log and sees if there's anything written to the log that hasn't been written to disk. And those things need to be redone, which means you take the log record that includes the change, you apply that log record to the old page, which is on disk currently, and then you write out the new page. So you get the new state out of this. And then when you want to undo, well, it's the reverse. So you have the new state, you take the log record and use it to undo so that you get back to the previous state. And this is the fundamentals of transactional databases. So let's take a look a little bit at cloud-native database architecture and what we've done in AWS with Amazon Aurora. So first of all, the architecture in Aurora, the fundamental thing in Aurora is that we have separated compute from storage, which means that we can scale compute separately from storage, and we can optimize a whole lot of things along the lines of database performance, but also durability and availability. So the fundamental parts of Aurora is we have a primary read-write replica where you can issue both reads and writes, and you can add a number of read replicas where you can read the data, but you can't write. So there's a primary writer. And on the storage side, Aurora always writes to 6 copies of the data across 3 different availability zones. So when you issue a commit or generate a log record in Aurora, that log record is sent to 6 different copies of the data in 3 availability zones. And a transaction can only move forward and commit once at least 4 out of these copies have acted back to the primary node that it has received the data. And an important thing with the read replica is that the read replica shares the same underlying storage. And this is part of this. We talk about the split between compute and storage. So the read replicas don't have their separate storage. They use the same storage as the primary node. And what's important to note then is that the read replica can always read the state of a page as it expects it to be based on where it is in time. So the read replicas will lag the primary by some number of typically milliseconds. But they can always find the page that it needs to read if the page is not already in memory. And then you can auto-scale or manually, for that matter, scale read replicas. We support adding multiple read replicas in a single region, and we also support automatic scaling of the primary as well as read replicas using Aurora Serverless v2 that we announced at reInvent this year. And in addition, we also have a product called RDS Proxy, which you can use to support more connections to your database and offload a lot of the connection management that the database traditionally has to handle. The proxy can also help you with even faster failovers in case of a loss of a primary. So let's look at the Aurora I/O profile. This is an important thing to note with Aurora. So on the left, we have an example of a traditional relational database, in this case MySQL. And you can see there's a lot of arrows here going from the primary instance over to the secondary instance and then down into storage on each side. And the color of the arrows matters. So the color represents different types of I/O. So we can see this purple here is apparently log. So the thing we talked about before, log writes. Bin log, which is logical replication in MySQL. We have yellow, which is data pages. Pink, in this case, MySQL writes the data pages twice to make sure that half a page doesn't get written because of different sizes in atomic blocks getting written to a data store. And FRM files in MySQL is metadata. So you can see here, there's a lot of arrows going on between the primary and secondary instance and the storage tier on the MySQL side. And it's because it issues log writes and it issues writes to all of these other things like the data pages, for example, on checkpoint. So we can see there was a simple benchmark run here for 30 minutes, and the MySQL machine managed to push through 780,000 transactions, so an average of a little bit more than 7 IOs per transaction. If we look on the Aurora side, what's interesting is you can see there's only 2 colors used for IO. There is the purple, which is the log records, and then there is the yellow you can see down here on the right, which is data pages getting sent to Amazon S3 for backups. And why is this? Well, this is because only the log records that get generated are sent to Aurora Storage. And Aurora Storage can actually then generate the pages, the data pages automatically. So they don't need the data pages to get written from the primary instance. So that's part of where you can see that there is a split of the database into 2. Part of the database sits in the compute tier, if you will, and part of the database that manages the pages and generates the pages based on this do, redo, undo protocol sits on the storage tier. We can also see that we send log records to the read replicas, and that's because the read replicas do use the same storage tier, but the read replicas have to be able to update the data that they have already in their buffer pool. So log records are sent to them, and they check if I have this page in the buffer pool, then I'll apply it and update the buffer pool. If I don't have it, I can just discard the page that I get replicated because I don't need it. If I'm going to read that page later, I'll read it from the shared storage. And here you can see again that this these 6 copies here, or 6 nodes, that represents the 6 copies of the data across the 3 availability zones. What's important to note is it's not only 6 nodes that support your whole Aurora instance. So every time you create an Aurora database, we create a number of sets of 6 nodes to represent your storage. So by default, when you create an Aurora instance, it's actually 16 times 6 nodes that will support your instance. And then every time your database grows beyond a certain size, we add another set of 16 partition sets, if you will, or we call them protection groups. A protection group is a set of 6 partition segments. So if we zoom into one of the storage nodes, and again, this applies to global database, which is why I want to cover it here. You can see this is the code basically that runs, or the logic that runs inside each of those storage nodes that we saw beneath the compute here on the previous slide. So you can see the database instance being the primary node sends log records to the storage node. It takes the log records in, puts them into memory, and then it then tries to write them to local disk SSD on the storage tier as fast as possible. As soon as it's just written the log record to disk, it knows the log record is safe, and it sends an ACK back to the database instance. That's the only thing that happens synchronously, if you will, on the storage tier. Everything else after step 2 here, if you will, is asynchronous. The primary node doesn't have to wait for it. So if you imagine then the primary node sent 6 requests out to the 6 copies. Each storage node took in a request, went through this process 1 and 2, sent back the ACK, and as soon as the database instance has at least 4 ACKs, it knows now the data is safe. I have quorum written to the 6 copies. It can move further, so it can continue moving. And also it might be worth noting that it sends multiples of these in parallel. It only has to actually stop and wait once it's waiting for a commit. So what happens after we persisted it? Well, step 3 here, you can see we then need to make sure that we have all of the log records we need in sequence. Because if we're missing one log record, the undo redo protocol won't work, right? So if there is a log record missing, so we have maybe log record 5 and 6, but 5 and 7, but we have 6 is missing, then we use a gossip protocol. So we go talk to our peer storage nodes. So there are 5 other copies, if you will, and ask, hey, I'm missing 6. Do one of you have it? Oh, I have it. Here you go. And then it can move forward. So it keeps checking that we have no holes in the list of log records, if you will. And then every once in a while, we go and generate data pages. So this is kind of like checkpoint in the traditional database. So we generate the data page so that we can quickly get it if a compute node asks for it, either the primary or read replica. If a read replica or primary comes in and asks for a page that we haven't yet generated, then we'll do it on the fly. And this is also why we keep generating them, because if we always did it on the fly, it would be too slow, because it takes obviously some time to apply and generate the data page. And then periodically we stage log and new page versions to S3 so that we can do point-in-time recovery as well as snapshot backups. And periodically remove old versions that we don't need anymore, and also validate consistency of the data pages that we have. So that gives you a sense of what goes on each of these little storage nodes. And what's interesting to note here is they, other than the gossip protocol and the incoming log records from the primary, they don't need to talk to each other. They're completely self-reliant, if you will. Okay, so then we have a little bit of an intro into Aurora and databases. Let's go into global database and see what we're doing there and what that's all about. So there are 2 primary use cases for global database. One is disaster recovery, and one is data locality, or bringing data closer to users. So in terms of disaster recovery, what's the use case here? Well, it's basically a region going down, having a catastrophic failure, and we need to get up and running as fast as possible in another place. So in this example, we can see we have a writer and reader in the US East region, and we're replicating to EU West. So in this case, if US East goes down, or network or something happens that is severe enough, you can switch over to EU West and continue running your operations here. One thing that's important to note, that's a difference between the local storage nodes, if you will, that I just talked about for Aurora and Global Database, is that the the storage that happens within the region is all synchronous replication. Like I said, the primary node will wait for at least 4 storage nodes to act before it moves forward. So it's completely synchronous. There's no risk of data loss. Whereas between regions, you have larger latencies. So global database goes after the disaster recovery use case, which is you may incur data loss. Generally, we're not far behind, but if there's a disaster, you have to make a choice. Do I want to bring up this region as primary and continue running my workload, knowing that there might be some data missing? So RPO is not 0 in this case, recovery point objective. The other use case is bringing data closer to users. So in this case, again, we have the primary in US East, but we also have readers in US West, EU West, and AP Southeast. And the thought here is that if I want to run an app and do reads or do reporting in these other regions than where my primary is, I don't want to incur the latency or potentially the cost of having all of the readers go to the primary node. I would rather replicate the data so it's local, if you will, so that I can serve these workloads faster. So this is more of a performance use case, if you will, versus the disaster recovery use case. So if we look at, zoom in here a little bit into what you can do with Aurora Global Database. Here we have this setup where we have the primary in the Ohio region, and the app is running against the primary, probably doing both reads and writes. And we have the storage tier that replicates the data to the Oregon region, as well as to Northern Virginia and to Ireland. And this replication then gives you support for up to 5 secondary regions. So you can have a total of 6 regions in your global database setup, a primary and 5 secondaries. And generally, this depends a little bit on the region and the distances, but generally you will have less than 1 second cross-region lag, which is your then risk of losing data, if you will, for the disaster recovery use case, up to 1 second, and generally not guaranteed. And that's also if you're running reports or applications against these for the other use case, that's how old data or how fresh the data will be for those requests. And then you get fast recovery. So this is an important note that if this disaster recovery happens or this disaster happens, making the secondary region primary generally takes less than 1 minute. So that's important compared to, for example, going and trying to restore backups, which will take more time. And Aurora Global Database supports very high throughput, which is generally a problem with these types of configurations across regions. It's up to 150,000 writes per second. So, and very negligible performance impact. And this is again because you can see the storage tier is what does the replication. It's not the primary node. So if you go back to the previous slides, the primary node keeps writing to the storage nodes, 4 need to act and so on, and it keeps moving. At the same time, you have a replication service that then starts sending these log records to the secondary regions. And that there's no additional cost, by the way, in terms of compute for this replication service that you see. You pay for data. There's a data transfer rate that you pay for with global database, but there's no additional compute nodes that you need to run or pay for. Okay, so what about read replicas in global database? Well, across the 6 regions, so the primary region and the 5 secondary region, we support up to 90 read replicas, which means you can have a very large read throughput globally across a single global database copy. So let's go in a little bit more into detail about how global database replication works. So first of all, the primary instance sends log records, as we said before, in parallel to storage nodes, and now includes the replication service as if it were one of the storage nodes. And then the replication service, in turn, can send the log records in parallel to a replication agent on the other side. And again, this is completely separate from your primary node, so this is not additional compute capacity, if you will, that you have to plan or pay for outside of the global database transfer fees. And then on the secondary side, well, the replication agent just acts as a primary. So it sends the log records to all of the storage nodes so they can go through and apply, just like we talked about in the zoom in slide, if you will. And it sends it to the read replicas so that they can update any buffer pool pages that they have. And you can notice also Amazon S3, you have now separate backups that happen on the secondary region, and you can configure backups there. So you can have separate backups set up, including point-in-time recovery up to 35 days, and do snapshots. So you can have cross-region backups also as part of Global Database. So step 4 is, if the replication server doesn't have log records, it's kind of like this gossip protocol for the storage node. It pulls log records it's missing from the storage nodes. There we go. So what about performance? Well, like I mentioned, we can support up to 150,000 writes per second. And here we see a comparison between logical or also non-parallel cross-region replication, which you see on the left side, versus the physical replication that Global Database is based on the right side. So you can see on the logical replication, the x-axis is just time, and the y-axis is queries per second. And you can see that the queries per second, as we ramp it up, the lag that you can see on the secondary y-axis keeps going up. And when we got up to closing in on 50,000 queries per second, or QPS, we're now up to closing in on 10 minutes worth of replica lag, which is also, one is, can be part of your RPO risk of missing up to 10 minutes data, depending on how the replication is built. It's also, you see 10 minutes old data on the secondary side, and you're handling, in this case, up to something like 40,000 writes per second. If we go on the right side and look at Global Database, you can see that the QPS ramps up here to about 200,000 writes per second. And the replica lag, you can see, stays well below 1 second. So here we hardly ever go over half a second in terms of lag. So again, this affects both your RPO, recovery point objective, as well as the freshness of the data on the secondary side. So let's take now a look at Global Database write forwarding. So what is that? Well, let's start with the use case. It's all about easier application development. So if we look at this, bringing data closer to users that we talked about before, what about if the user needs to write? So in this case, I have readers in multiple regions, but I also now apparently want the EU West region to be able to write. So how do I handle this? Well, without write forwarding, the app needs to know that if it needs to write, it needs to connect to the primary region, and it needs to have a way to connect there, and then it can issue the writes. So that just increases complexity in configuring the app, configuring network security, and so on, and in just writing the app, if you will, the application code. So what does write forwarding give you? Well, it enables you to simply connect to a reader and issue writes. So you can issue transactions to the reader. There's a configuration setting you set on the session level, and once you set that, you can issue writes. And so how does this work? Is it consistent and so on? Well, we have a setting on how to handle consistency, but there's no risk of things like conflicts, because the write only happens on the primary. What we do is we forward the write directly from the reader node to the primary. And you can see we try to show here also we don't go through the storage tier here. We forward it to the primary. The primary applies the write, generates log records. Those get synced back to the reader, and it can now see the data. And you can then configure the reader depending on your performance requirements to say, hey, just send it to the primary. I want to know that it's safe. There's no non-durable option here. So send it, wait for an ACK back from the primary, and then continue. That's good for performance. There's obviously the lag of us sending the request to the primary, but that's about it. And obviously the primary applying the change as well. The downside here is when you go read, if you issue an insert, if you try to read it immediately after, you may not be able to see it because the replication hasn't caught up yet. So you can also configure it to say, hey, I want to be able to read what I wrote. So I wait. So we will wait until the log record is there, and then we will commit with the reading. And that's probably what is most useful to most applications. So we have different levels of consistency that you can set here. But it's important to note, all consistency levels are durable, and there's never a risk of write or merge conflicts or anything like this. And should also mention, this is supported on Aurora MySQL today, not yet on Aurora PostgreSQL. So let's talk about Global Database Managed Recovery Point Objective. So here, again, the recovery point objective is basically in case of a disaster, how much data do I risk losing in terms of amount of time? And as I said before, generally global database will not be behind me more than typically less than a second. So then your RPO is basically less than a second. However, there's obviously a risk, there's some network glitch or something happens which could increase your RPO and your risk of data loss. And then what will happen with global database by default? Well, we will keep writing to the storage nodes and to the replication service, but it will not be able to send it to the region, to the secondary region. So it will keep trying, and at some point the secondary region connects again, and then it tries to catch up, and it doesn't try to, it catches up, and then we're all fine. But you are then at risk for some amount of time here when you have an increased lag. So what can you do about this? Well, on Aurora PostgreSQL, so in this case we supported first on Aurora PostgreSQL, and it's on our roadmap for MySQL, we have this configuration that's called Manage RPO. And what you do is you basically tell the cluster, how far am I okay to be behind in at least one of my secondary regions has to be within this RPO. As long as one of them is fine, I know I'm protected. So let's take a look at what we could do here. So in this case, in the example, we've set the RPO to 20 seconds, which basically means I'm okay, potentially in case of a disaster, losing up to 20 seconds of data, but not more. That's what it means. So how does this behave? Well, in this case, everything is fine, because if you look at the two regions, I have Northern Virginia and Ireland here as secondaries, and I have Ohio as my primary. The RPO lag for Ireland is apparently 5 seconds, but the Northern Virginia has gone to 22 seconds. Well, I'm still fine because I'm protected by Ireland. Ireland is within 20 seconds of lag. Now, also, Ireland went to 21 seconds. So apparently the lag is now 30 seconds in Northern Virginia and 21 seconds in Ireland. And I'm no longer within my RPO requirement of 20 seconds. So how does Aurora handle this? Well, we basically pause any commit acts being sent back to the application. So the application can write, or try to write if you will, but as soon as a commit happens, it will Aurora Storage will wait, because we're outside of our RPO guarantee, which means the application will wait for the database request. It will look like the database write has hung until we're within the RPO. And obviously there might be a timeout in the app, so the app might say, okay, at some point we timed out on the write operation and it aborts. Okay. And then as soon as, in this case, Ireland is within the 20 second, or Northern Virginia for that matter, but in this example, Ireland is now within 20 seconds, immediately we resume and we issue all of those acts back to the client. So now the client can continue writing again. But this way, as you can see, we guarantee that we will never act back a commit to you where there's a risk of losing, in this case, more than 20 seconds of data. And setting this RPO is obviously something that I think takes customers quite a bit of time of thinking. So do you want to prioritize availability of your app? Because as soon as the writes stop, your app will grind to a halt when it comes to writes. Or do you want to risk data loss? And this is something that every app you have to look at, what's the right setting for that app. And many apps will want our default behavior, which is never stop the availability of the app in case of a secondary region falling behind, or multiple in this case. Okay, finally, I want to cover global database managed planned failover, which is on our roadmap for 2021, so hopefully coming soon. And what does that mean? Well, today when you set up global database, you can't move the primary region. So the primary region is always the one you start at. So, okay, if I can't move it, what does that mean in case of a disaster? Well, in case of a disaster, you can go to a secondary region and you can disconnect it from global database. And now it's a regular primary, and you can start using it as your new primary. So that works well for a disaster recovery scenario. But if you want to do, for example, a disaster recovery drill, Or for performance circumstances, maybe you have this distributed read use case. You may want to move your primary to a secondary region. You have to basically disconnect global database, decide in your app that this is now the primary, make sure your app writes to the primary and stop the one that used to be the old primary, and then configure global database again and will replicate all of the data again. So this is a bit of a pain, obviously. And that's what global database managed plan failover is all about. It's basically you being able to say, now I want to move my primary from this region to that region. And Aurora takes care of all of the heavy lifting. And this will be available, as you can see on the slide, both for Aurora MySQL and Aurora PostgreSQL at the same time. So how does it work? Well, I have my setup again with Ohio, Northern Virginia, and Ireland, and the app is running against Ohio in this case. And now, because of some reason, probably the most common thing here is that you want to test out your disaster recovery solution. So this is a disaster recovery drill. You're moving your app over to Northern Virginia in this case to verify that your disaster recovery plan works and is fast enough for your business. So we click to promote Northern Virginia to be the new primary region. Then Ohio writes are stopped. So we make sure that we drain Ohio so we never lose any data. This is managed for you. And then the secondary regions both catch up to make sure they got all of the writes that happened in Ohio, synchronously now, if you will. And then Northern Virginia now becomes the new primary. So now it is the primary and it can accept the write workload. So writes are now available in Northern Virginia. It's the new primary. And then you now need to point your app to the Northern Virginia endpoint and you're good to go. So everything here is managed for you. Outside of your app has to now be changed to connect to Northern Virginia for its writes. So that is managed planned failover. And again, it's on the roadmap and hopefully coming very soon. We have some related sections, so that's it for global database. Hopefully you got a bit of insight into this. Definitely recommend that you play around with the feature. This is super powerful, both for disaster recovery use cases, for use cases where you want to make faster reads for secondary regions, as well as for cross-region backups. Like I mentioned, you can have a secondary global database region and have a separate backup schedule there. And those backups are completely separate from your backups in the primary region. So I recommend a few other sessions that you take a look at. One is transforming Hilton's reservation system with Amazon Aurora PostgreSQL. This is a presentation by Hilton. We have Amazon Aurora Storage Mystified that Anupriya Mathur presented on a bit earlier in reInvent. So that session is ready for you to go and take a look at. And then finally, Kathy has a presentation on how Amazon Aurora helps you protect your data from mistakes. So that sounds pretty interesting. I also recommend that you go watch that. With that, thanks a lot for watching. Hopefully you got a bit of insights into what we're doing with Aurora and especially global database. Thanks a lot.